told us that whether you do Turing reductions or many one reductions, mostly somehow you can sweep it under the rug. Apparently that, except for that sometimes you cannot, I think, and this is maybe what Noah is going to tell us about. So without further ado, please.
Yeah. Okay. Yeah. So Robert set me up beautifully for this. So we're going to be talking about our new paper showing that this PPP class, corresponding to the Pigeonhole Principle, doesn't behave the same way under Turing reductions in many reductions. This is joint work with Stefan Grosser, Robert Robert, and Tony Tasky. Here we go. Okay. Yeah, so we're going to be looking again at this pigeon problem. So I'm just going to think about it as a map from n things to n-1 things. You know, it's encoded as a circuit, so we're working over an exponential size universe. But yeah, again, it'll just be like in Robert's talk, where we have a map from n things to n-1 things. We're going to think of the domain as pigeons and the range as holes, and you can query this map to ask where like the ith pigeon maps to. And since there's n-1 holes, we want to find a collision. So a pair of pigeons that are distinct that map to the same hole. Like this. Okay, so this is a TFNP, it's total. And given any pair of solutions, you can check where they map to the same hole efficiently. And it's the complete problem for the class PPP. Which is like one of the original 5 TFNP classes, lies there in the hierarchy, so it's fairly high up. And it's been extensively studied because it has like deep connections to a lot of problems in cryptography and lattices. And so, for example, finding collisions in hash functions, a bunch of variants of the discrete log problem, Blichfeld's theorem in lattices, and factoring if you assume the generalized Riemann hypothesis, otherwise it's randomized reducible to pigeon. And it's also important for proof complexity. You know, the Pigeonhole Principle has been like one of the most valuable theorems for us to study for proving lower bounds. So really understanding the complexity of this class PPP is, you know, pretty valuable. So unlike all of the other major TFNP classes that we've looked at, PPP appears to be a lot less robust. So in particular, Buss and Johnson and also Daskalakis conjectured that PPP is not closed under Turing reductions. So, you know, what does it mean to be closed under Turing reductions? Well, roughly it just means that if I can solve a problem by many calls to pigeon, you have a problem R, take an input, you define an instance of pigeon, solve that instance, define a new instance, so on and so forth, finally get a solution to R. Then this means that it's many one reducible to pigeon, so you can solve it with a single call. So every other major TFNP class is closed under Turing reductions. It's not too difficult to see. So yeah, so the question is like, can we show that PPP isn't as well behaved as these other classes? So there's one obvious issue here, which Robert mentioned, which is that the separation between any TFNP classes would imply P is different from NP. So in particular, separating PPP from its Turing closure in the standard white box model, which would imply this separation. So we can't really hope to do that at the moment. So because of this, Buss and Johnson asked to give evidence for the fact that PPP is not Turing closed by proving a black box separation. And that's the main result of this work. It's show that PPP is not closed under Turing reductions. And in the rest of this talk, I'm going to kind of give you a flavor of our proof because I think it's really cool and it has like deep connections to proof complexity. So we're going to use tools from proof complexity in kind of new ways in order to show this. So the first thing we need to do is find a candidate problem, which is in the Turing closure, but not obviously in PPP. And we're going to use kind of the simplest problem that it's not obvious how to solve with PPP, which is this pigeon squared problem. So now you're given, instead of one instance of pigeon, you're given two instances, and you want to produce a solution to both of them. So, for example, there's a solution, you solve the left instance, you solve the right instance, and you output like the concatenation of the two solutions. So it's easy to see that this is in the Turing closure. Just solve the two instances in parallel, produce the solution. There you go. And it's actually in it's something that's like weaker than Turing closure, called the like non-adaptive Turing closure, where in the standard Turing closure, or Turing reduction, you can solve an instance of pigeon, then define a new one based on the solution that you got. Here, you have to solve all of the instances of pigeon in parallel. And our main theorem is that this pigeon squared problem is not in PPP. So we kind of separate PPP from its Turing closure in a very strong way. We also separate it from the non-adaptive. Okay, so how do we do this? So yeah, we're going to adapt techniques from proof complexity. As Robert mentioned, there's this very close relationship between black box TFNP and proof complexity. So here's the standard list of TFNP classes, and we have a bunch of characterizations of these TFNP classes by various proof systems. And you can see right in the middle, here's PPP. And as Robert mentioned, we don't have a natural like proof system that corresponds to PPP. We can construct one by this result with Sam and Russell, but it's very artificial. So we actually came about this PPP Turing closure problem by trying to show that if a TFNP class is not closed under Turing reductions, then it doesn't really correspond to a natural proof system. Doesn't really seem to be true. So it's still an open question. So in order to prove our separation, we're going to look at kind of zoom in on these three. So here at the bottom, we have this class PPADS, which is characterized by the Shirali-Adams proof system in the following sense, that a search problem is in this class PPADS if and only if there's a low degree Shirali-Adams proof of the totality of the search problem. Just caveat that its coefficients can be measured in unary, but it's not super important. And then it's sandwiched above by sum of squares. We know that sum of squares can prove the Pigeonhole Principle. This containment, at least at the bottom, is strict. So it's well known that Shirali-Adams cannot prove the Pigeonhole Principle. Okay. So the idea is to take the standard
low degree Shirali.
Yes, in low degree, yeah, you can prove it in low size. Yeah. So the idea here is we're going to take the lower bound technique for Shirali-Adams, and we're going to strengthen it a little bit in order to prove our separation. Okay. So for those of you who have worked with Shirali-Adams before, usually if you are going to prove lower bounds on it, you're going to work with its dual characterization. So there's these objects called pseudoexpectations, and the existence of a pseudoexpectation like precludes the existence of a degree Shirali-Adams proof. Here we're going to focus on this pigeon square problem. So what's a pseudoexpectation? So it's an object that works over polynomials, and we're going to be looking at like multilinear polynomials. That is, x squared is equal to x, so every variable has power 1, 0. And sort of a pseudo expectation is an object that looks like a true distribution when you look only at degree d moments. And for this pigeon squared problem, it's going to look like a true distribution over matchings from like n pigeons to n-1 holes, so something that doesn't exist, but only when you look at moments up to degree d. So we can define it formally, which is as follows. It's a linear map from polynomials, the moments of the distribution. such that if you look at conjunctions of degree at most d, so a conjunct is just like it's just a junta, so it's x, 1 minus y, z, something like that. It's going to satisfy the following properties, which basically is enforcing that on the degree d moments, it behaves like a true expectation. So conjuncts are non-negative for degree at most d conjuncts. It's normalized. And then finally, it needs something where it actually depends on this pigeon squared problem, which is that it like doesn't witness a solution. So we're saying that it never sees a collision of two pigeons here. Sorry. So what do I mean by it doesn't witness a solution? Well, I'm going to say that a conjunct witnesses a solution if it like contains the indicator of a solution to this pigeon squared problem. So it contains the indicator of two pigeons mapping to the same hole in both cases. So here's a little example. It contains this indicator of pigeon 1 mapping to hole 3, pigeon 3 mapping to hole 3 is this collision, and also this collision. So for any conjunct which contains such an indicator, it sets the expectation value to 0. So it never sees these things. So again, it's an object that looks like the moments of a distribution, which never sees a matching. Or which only looks at like matchings from n pigeons to n minus 1.
So the totality is somehow, so every pigeon flies to a hole is somehow enforced?
Yeah, so this is like, so these pseudo expectations are going to like preclude the existence of Shirley-Adams proofs. So this is basically like an object that's saying that this pigeon squared problem is not total. That's kind of what it's.
I think
encoded in binary. Oh, yeah. Yeah, so what these things mean is this is like the indicator, write it in binary, you get a conjunct. Yeah, I kind of wanted to sweep that mess under the rug. But yeah, you can write that down as like Boolean variables.
Sorry, so if you have Boolean variables, how's this different from saying that you've got this product P13, P33, PQ0 to Q12?
So are you just asking about like, you take this thing here and you'd have log n many variables for P1 and you'd enforce that.
Oh,
like
it's the binary, sorry, this is the binary
Oh,
encoded.
yes, so this is the binary encoding of the Pigeonhole. Yes, I should have mentioned. Yeah, any other questions about this? Yeah, so we want to take this pseudo expectation and use it in order to separate pigeon from pigeon squared. So there's a problem with just applying it directly, which is that Shirley-Adams can't prove the pigeonhole principle or the binary pigeonhole principle. And so there exists a pseudo expectation for both of these things. The pseudo expectation lies down here. So what we're going to do is we're going to take the definition of a pseudo expectation and strengthen it somehow, so that it separates pigeon from pigeon squared. So it lies instead up here. This is going to be our collision-free pseudo expectation. So a collision-free pseudo expectation is going to be a standard pseudo expectation with some additional properties, which means that it doesn't exist for pigeon, but it does exist for the pigeon squared problem. And the way we're going to come up with these additional properties we're going to add to the pseudo expectation is by, we're going to suppose that we actually had a reduction from pigeon squared to pigeon. We're going to look at what we need in order to contradict the existence of this reduction. Okay. So everybody good so far? Any questions? Okay, so let's suppose that we have a reduction from pigeon squared to pigeon for contradiction. So each of these reductions given by n decision trees, one for defining where each pigeon flies. For simplicity, I'm not going to assume that we have like output decision trees. We have decision trees mapping an input to pigeon squared to pigeon. I'm not going to look at decision trees mapping solutions back. It'll just make things a little bit easier. And we have the following correctness property for our reduction, which is that if we have any solution, if we have an input for the pigeon squared problem, then these decision trees define a new input for the pigeon problem, such that if there's a collision in the pigeon problem, something like this, then this has to be then a solution for the pigeon squared. So in particular, I'm ignoring mappings back from solutions to pigeon squared, from pigeon to pigeon squared. I'm just going to enforce that alpha, like the assignment to pigeon squared, actually has to contain a solution.
So the partial assignment.
Yes. Yes. For it, yes, the source functions. Yeah. So that's what I'm going to look at for now. It's a little simplified assumption. So this is the correctness property we have, and this is what I'm going to use in order to generate these, like the conditions we're going to need in order to strengthen this pseudoexpectation. Suppose we have this reduction. So each pigeon in the reduced to pigeon instance is then defined by a little decision tree here, querying the variables of pigeon squared. So these are the queries. So maybe it asks where pigeon 2 in the pigeon squared instance goes to, and it believes it's down to the holes. Kind of the high level idea of how we're going to construct these collision-free pseudo-expectations comes from the standard proof of, or the standard refutation of the Pigeonhole Principle. So in the Pigeonhole Principle, like if you prove it in sum of squares, what you do is you argue first that each hole receives at most each hole receives at most one pigeon, then you sum up the number of pigeons, sum up the number of holes, you get n is equal to n minus 1, you get a contradiction. So our collision-free pseudo-expectation is going to require that every hole receive at most one pigeon. Okay, so we have this reduction from pigeon squared to pigeon. We're going to think about the decision trees in this reduction as a set of root to leaf paths, or equivalently a set of conjunctions. And we're going to look at all conjunctions which map a pigeon to a particular hole. So in the decision tree for pigeon I, we're going to look at all paths which send a pigeon I to a hole j. So this is going to be this hij set. So here H31 for this decision tree here, it's telling us where pigeon 3 maps. And the 1 here is asking about all paths which map it to hole 1. So we get these two paths here. It's the two paths in red, like that. So that's our set H31, and we're actually going to be interested in just this set Hj, which is just like all paths in this reduction, which tell us that some pigeon goes to hole j. So this is really the object that I'm going to care about. This Hj set, which is just like all paths in our reduction, which map a pigeon to hole j. Think about our set of conjuncts, which tell us that a pigeon goes to hole j. And the key property that we're going to look at from this set is that for any pair of paths which map a pigeon to the same hole, they're either inconsistent, meaning that the paths like map one pigeon to two different holes. In the pigeon squared instance. So these are it's a little confusing because they're on the variables of pigeon squared. So either these paths are inconsistent, so like they're formally the zero polynomial, or they witness a solution to pigeon squared. And this follows by correctness. So if Hj contains all paths which map pigeons to hole J. So if they map two pigeons to hole J, then by correctness here, they have to have witnessed a solution to the pigeon squared problem, just by the correctness of the reduction. So that's what this is telling us. So from this correctness, we get this property on the set of paths which map pigeons to hole J.
So the piece that's a little kind of, okay, so right, so if you're in the second case, you're not inconsistent. You just, you basically, you just have to give the correct answer. That's all you care about. Like, there's nothing special about the fact that it's combined of.
Yeah, no, it's just like if you're seeing a solution to the reduced to instance, then you have better have gotten a solution to the original.
Because these are just, the PNP prime really are a witness to the supposed pigeon problem that's doing the reduction. And so
Exactly.
you found a collision, that collision better tell you what the answer to both of the original pigeon problems.
Exactly.
Okay.
Yes, it's just follows by correctness. Yeah. So
Okay.
this is the key property here. I'm going to say that a family of conjunctions or a family of paths in these decision trees is pairwise witnessing that satisfies these two conditions. For every pair of paths in this family, they're either inconsistent or they witness a solution to the original. Okay, so now we can define what this pseudo expectation operator is. So it's the standard pseudo expectations. This is just the thing as before. But we're also going to enforce the additional property that's basically saying that every hole is going to get at most one pigeon, as I'll show you in a minute. Or equivalently, they select for any pairwise witnessing family, that is any family of conjuncts or family of paths that satisfy these two conditions, the mass is at most one. Okay, so let's see that this works. So if there's a reduction from so if there exists one of these pairwise or these collision-free pseudo expectations, then there can't be a reduction for pigeon squared to pigeon. Yeah.
I go to this collision-free pseudo expectation is for pigeon squared or for pigeon?
It's defined over the variables of pigeon squared. Yeah. So it's going to preclude the reduction, the existence of reduction for pigeon squared to pigeon, and let's just see that really quickly. So suppose there is such a reduction. These are each polylog n depth decision trees according to variables of pigeon squared. And what we're going to use is this property here that for each pairwise witnessing family, its mass is at most one, where a pairwise, and we're going to use the fact that HJ is a pairwise witnessing family, where HJ is like all paths which map a pigeon to hole J. Okay. So let's see that this the existence of one of these things contradicts such a reduction. So let's pick any of our decision trees in our reduction, and just like the standard fact of a decision tree is if you sum over all paths in a decision tree, it's like the formally one polynomial. Nothing magic there. So if I apply the expectation operator to it, because the expectation operator is linear and normalized, we get this. Now summing over all overall pigeons, we're going to get this here. So what I'm doing is I'm basically doing that proof where you sum up the number of holes, sum up the number of pigeons, and you get two different numbers. Okay, so now I'm going to partition according to the number of holes here. So I'm going to look at all the paths which map a pigeon to a hole J here, so this HJ here, and by the key property, we know that HJ is one of these pairwise witnessing families. So by collision freeness, its mass is at most one. So we get this is at most one. This is n minus one contradiction. So really what this is saying is that we're going to enforce that this reduction at most each hole is going to get each hole is gonna get at least one pigeon.
Yeah, so the statement we really want is for every polylog n bound, if, if you can get such one of these things for every polylog n bound, then you get the consequence. So
Yeah.
it's not just for some collision, you need it for all polylog n such
Yes.
bounds. There's actually kind of a universal thing in that if portion.
Yes. Yeah, okay, so I think I'm basically out of time, but I can just say a word on how we actually construct these pseudo expectations. So if such a pseudo expectation exists, then it separates pigeon from pigeon squared. And so now we actually have to show that one of these exists, and this is kind of the main work in the paper. So we want to create an object that looks like, one of these pseudo expectations. So it looks like the moments of a degree D distribution with matchings from n pigeons into n-1 holes. And so we're just going to take the standard pseudo expectation for pigeonhole to be our expectation. So for any conjunct, if that conjunct witnesses is a matching, then we'll set it to be the second one. We'll set it to be the uniformly random probability of that matching. And if the conjunct does not witness a matching, if it sees like a collision, we'll just set it to be probability 0. Okay, so it's going to satisfy these first three ones. This is just exactly the same as the pigeonhole lower bound for Shirley-Adams. There's nothing special there. The last thing we need to satisfy is this collision freeness. That's again where the main body of the work is. So the very last slide is the high level of how to prove this collision freeness. We're going to show that from one of these pairwise witnessing families, we can construct a matching decision tree. So this here, the main thing I wanted to say is just that we're going to use ideas from this old paper, which shows that the Pigeonhole Principle lower bound for AC0 Frege. So there they use these matching decision trees, which are like a key component. So we're going to use these. And then finally, we're going to need to show that the expectation of one of these matching decision trees from pairwise witnessing family is at most 1. Okay, and this is just like a careful decomposition argument of these decision trees. Yeah, I'll leave the paper for the fun techniques. Thanks.
So PLS is closed under Turing reductions.